In this video, we're going to review how to write skeleton equations and word equations for chemical reactions. Afterwards, we'll take a look at how to balance chemical reactions. So as a quick refresher, remember that in a chemical reaction, you start off with something called reactants. Reactants are the substances that you start off with, and then afterwards, when they react, they are converted into products. So that's what's made in the end. So for example, if we have the reaction A plus B, arrow C, the reactants on the left side here, these are the reactants, they are starting materials, and then C is your product, what you end up with. And typically we have an arrow that means to produce, and on the left side you have your reactants, right side you have your products. So a quick little reminder about chemical reactions. During the chemical reactions, you have elements and compounds, and what they'll do is they'll interact with each other. And it could be elements reacting with elements, compounds reacting with compounds, compounds reacting with elements, a mix of those. They're going to interact with each other to form new substances. We've rearranged the atoms and the bonds, and we have new substances that form. So it's not just a matter of change of state, but rather new substances have actually formed. And so we've seen already in a previous review that there's certain clues that a chemical reaction occurred. For example, you might have a color change, so the new substance has a different color. You might have the formation of a precipitate, as you can see over here, and here we see the color change. You might have a formation of a gas. You typically see bubbling that happens. You might have a new liquid that forms. Sometimes when two solids react, you'll see a liquid forming. So that's a possibility as well. You might have a change in the energy. So you might have the reaction starting to feel hotter or colder, because when you mix the reactants together, they release energy or absorb energy. You might have a change in the odor or the taste. And we also saw with energy that you might also see energy can be released as light, for example. So there's various clues that you can take a look at to see that a chemical change is happening. You just have to make sure that those clues are actually a result of a new substance being formed. So rather than write long paragraphs and essays about a chemical reaction, we like to simplify things a bit and write equations to represent those chemical reactions. And so there's several types of equations that you can write to simplify what we're doing. One type is called a word equation, where you represent the reactants and the products using, well, words, using their names, using the ionic compound name and molecular compound name, or whatever be the case. So here we have an example of a word equation. We have carbon dioxide plus water, arrow, oxygen plus glucose. And so the carbon dioxide and the water, they're on the left side of this arrow here. So they're the reactants, they're your starting materials. The plus over here means reacts with. So carbon dioxide reacts with water. The arrow means to produce. And then oxygen and glucose. So the plus here means and. And oxygen and glucose are on the right side of your arrow. So they're the products. So this is what all the different symbols within a word equation mean. So we're going to practice identifying reactants and products from descriptions, and then from that we're going to write some word equations. So here we have sodium metal and chlorine gas react to form solid sodium chloride. Write a word equation for this reaction. So when you write a word equation, a couple things I want to mention is that you typically don't put the class or the state for substances. So just keep that in mind. We might put that in the description, but we won't put it in our word equation. So here, identify the reactants in the description provided. So sodium and chlorine are reacting. So it's sodium, that's one reactant. And the other one is chlorine. And identify the product or products. So what's formed, that's the key word here, sodium chloride. Sodium chloride, that's a compound. So now what you can do is you can take these pieces and make a word equation. Notice I didn't put the states in when it comes to word equations. So all I do is put my reactants on the left side, so sodium and chlorine. Don't put and, put plus to represent and, chlorine, because we want to simplify this as much as possible. We want to make this universal for everyone to understand. I mean, we're still in the English language here, so this is not as universal as it could be. There's a better way to do that, and we'll see soon. But they're reacting to produce sodium chloride. So this is more efficient than having to read through a long description, and this wasn't even the longest that I could get. I can get much longer than that. Um, but we can be more efficient than that. We can be a little bit, let's just say, lazier than that. We can, instead of using words, make this more universal and use, well, that's right, they're symbols. And so when we decide to go from a word equation to symbols and to formulas, we call that a skeleton equation. A skeleton equation. So we're going to see how to convert word equations to skeleton equations. So here we have an example of a skeleton equation. Rather than represent the reactants and products as words, we use their symbols and formulas. A lot of the stuff is very similar. So the plus means on the reactant side means to react with. So CO2 reacts with water, and then the arrow still means to produce. So this to produce oxygen and glucose. So on the product side, the plus means and because that's something produced. The arrow means to produce or to form or yield. Yield is another way you can say it. Yields. And then another thing that's a bit different is that we actually show the states of matter and their and how they're existing. So if you see S in brackets next to the chemical, we know that means solid. L means liquid. G means gas. And then AQ means aqueous, which basically means dissolved in water. So when it comes to skeleton equations, you want to show those states if they're given to you in the question, or sometimes you might need to know what those states are. There's certain chemicals where you know what the states are for sure. So here we have, again, our reaction. Solid sodium metal and chlorine react to form sodium chloride, and we want to write a skeleton equation. So usually what I do, especially if this is the first time I'm doing this, is I'm going to write out a word equation first. I'm going to put sodium plus chlorine, arrow, sodium chloride. And now what I'm going to do is I'm going to convert this into a skeleton equation. I'm going to basically convert all these words into their symbols. So sodium is Na, and we're not given the state here. We're told this is sodium metal. Metal is not really a state, but typically you'd be provided with other information. Usually when you're dealing with sodium at room temperature, it's going to be a solid. So if you look at the periodic table, sodium in its periodic table is solid. Based on the color coding that we have in our periodic table, the black font indicates that it's solid at room temperature. And so typically I go with that. Chlorine, this is where you need to be careful. So there are some elements when you write them down, when they're alone, they're written down in their diatomic form. So remember Hofbrinkel? Whenever you see those alone, when they're not in a compound, you need to write them in their standard diatomic form with the 2 and then the state that's provided there. So chlorine, you can't just put Cl, you need to put Cl2 and then put a gas. Even though it doesn't say chlorine gas there, you need to know that's its standard form. So we have sodium, solid sodium there, reacting to produce reacting with chlorine gas to produce sodium chloride. To find the formula for sodium chloride, we just use our rules for naming and for writing formulas for compounds. This is ionic, so we need to do the crisscross, Na plus 1, Cl minus 1, crisscross it or charge balance, and you get NaCl. And don't forget over here, we're told the state of NaCl is solid. So notice I didn't put a 2 by the Cl there over here because this is not alone. This is in a compound, and we determined that subscript using the crisscross method or whatever formula method we use. The diatomic really only applies to when they're not in a compound. And so you need to have these memorized. You need to know when to place them. Don't forget there's also polyatomic. Phosphorus would be P4 solid. S8 would be, sulfur would be S8 solid when not in a compound. So we just converted a word equation to a skeleton equation. Let's do a few more examples. Here we have beryllium chloride reacting with aqueous silver nitrate in water, and that aqueous beryllium nitrate and silver chloride powder are made. So let's go ahead and write out a word equation first, and then we'll write out a skeleton equation after. So we have our reactants, because it says these are reacting together. Reacts with, that's our key term there. So it's aqueous beryllium chloride. We're not going to write it out as a word. We're not going to write out aqueous. We're just going to write out beryllium chloride. Beryllium chloride plus silver nitrate. I think I should have started more to the left of my screen, but that's okay. They're going to react to produce. Now, this is in water. That's not a reactant, okay? It's just saying that this is happening in a watery environment. When you make chemicals react, if they're aqueous, they're dissolved in water. So that's not a reactant, okay? So don't add plus water there, because these are happening in water. They're not reacting with water, though. And they're going to make beryllium nitrate. Plus silver chloride. So we wrote out our word equation. So this is WE, word equation. And now we're going to write out the skeleton equation. We're just going to convert these to their formulas. So crisscross method, because this is ionic. So we get BeCl2. We're told this is aqueous, and we need to put that down in the skeleton equation, AQ. Put the plus back where it was. Silver nitrate, you do your crisscross method because it's ionic, Ag, and then NO3AQ. Just a reminder, nitrate is your polyatomic ion, right? So you would do a crisscross, just showing you the work here. You don't really have to put this in the equation, but NO3 minus crisscross or charge balance, and you get AgNO3, aqueous. And then beryllium nitrate, same thing, crisscrossing to get this, aqueous. And then finally, silver chloride, AgCl, powder. So that's solid. And there we have our word equation and skeleton equation. Write word first so you don't get confused with the big description that's there, then convert it into the skeleton equation from there afterwards. So when isopropyl, so here's another example we'll do. When isopropanol reacts with oxygen gas, comma, carbon dioxide, water, and heat are produced. So let's write out a word equation first. So we have isopropanol reacting with oxygen. That's going to produce some carbon dioxide, plus water, and then also some heat. Some heat is released. So typically you can actually write heat in the reaction. It's not really going to affect your balancing. It's actually more important for grade 12 that you do that, but I'm going to put it in heat's produced or heat's released. So I'm going to put plus heat here. Okay, so I'll do that for now. And now what I'm going to do is I'm just going to convert this into a skeleton equation. So we had our word equation. Notice for some compounds, you may not know how to name them because you didn't learn those rules. So if there are compounds like that, I would provide them to you in brackets. So here we're going to convert isopropanol to C3H8O. And I didn't tell you the state here, but I'm just going to add it myself. Unless I told you, you wouldn't have known this. Typically, this will be in its liquid state at room temperature. You should know this one. Oxygen is O2 gas. Even if I didn't put gas here, you would have known that. And in these type of reactions, usually the products are going to be gas as well because they release lots of energy and things kind of evaporate. And carbon dioxide, it's usually a safe bet that it's going to be a gas unless you're told otherwise. In the water, if there's a lot of heat, would have probably evaporated and would have been in its gas form as well. And then you can put plus heat. So the states you should have known for sure: oxygen, carbon dioxide gas, good bet that it's going to be a gas unless otherwise stated. And then water in these type of reactions like this that are combustion, you're typically going to have gas as well. But again, the main ones I would focus on are these two here to know for sure. So let's go the other way. Let's convert these into word equations just to practice our naming a little bit. So you can try this yourself now. You can pause it, try it out yourself, and see if you can do this. So here, if I were to write a word equation, I would have aluminum plus oxygen are reacting. So aluminum reacts with oxygen to produce, and then I would name this as aluminum oxide. And then here, a bit of a longer one, so I might have to write a bit smaller. Here we have iron 3 oxide reacts with, this is H2SO4, sulfuric acid to produce iron 3 with our Roman numerals, 3 sulfate and water. You could write dihydrogen monoxide. Remember, water is one of those ones that we typically represent as a by its common name. So here's some more practice. You can try this one out yourself. Pause the video and then check your answer with me to make sure you're on the right track. So we have, during a driving collision, a sensor in the airbag detects that the vehicle has slowed down suddenly. In response, a small pellet of solid sodium azide is heated, producing harmless nitrogen gas and some solid sodium. So here we have sodium azide. So let's write our word equation out. This is our reactant, what we're starting off with. Sodium azide. And when the accident occurs or there's a collision, what we produce is some nitrogen gas. I'm just going to write nitrogen here, plus some sodium. Remember, you don't put the states in for word equations. Then for a skeleton equation, we can just convert these into their given formulas. So I'm going to put my arrow back where it is here. I'm going to write the ones I know for sure right away. Nitrogen is nitrogen gas, N2, one of those Hofbrinkel. Sodium is not a Hofbrinkel. And at room temperature is typically a solid. If you look at your periodic table, that color coding is a black font. So we know that it's a solid there. So those are produced there. Sodium azide, we told you that azide is a polyatomic ion. So essentially it's going to be, just to show you the work here, Na plus 1, and then N3 minus 1. And if you do the crisscross, you get Na1 and then N3 1. So this is sodium azide over here, Na, N3, and it's in its solid state in this reaction. So again, if you didn't have this polyatomic ion in your table that we give you for assessments, we would have provided to you in the question in some way. And so it's this gas here that's actually inflating the airbag, because when you have solid at first, it's confined in one small volume. It doesn't take up the entire space of its container, but once that nitrogen gas is produced, then it starts to take up the space of the container and then starts to inflate the airbag. So that's what you see in there, some nitrogen gas. Here's another practice problem for you to try out. You can pause the video and try it out yourself. So we have, we want to write out a word equation and a skeleton equation for this reaction. We have calcium and fluorine reacting to form calcium fluoride. So we're going to write out a word equation first. So we'll do that here. Word equation, calcium plus fluorine react to form calcium fluoride. So here we have calcium. I'm going to write my skeleton equation now. Calcium is a metal. Usually at room temperature, metals are solid. If you look at your periodic table, let's go take a look just in case you're not sure what I'm talking about here. If you look over here, all the black font is solid at room temperature. So we could assume that it's solid at room temperature here. All the red is gas at room temperature, and all the blue is liquid at room temperature. So let's go back and finish that up. So we're going to have our calcium is solid. Fluorine is F2. It's one of the Hofbrinkel gas. And then we have calcium fluoride. We need to figure out the formula for calcium fluoride using our crisscross method. So we have plus 2 here, F minus 1, crisscross it, and you get Ca, F2. Generally, at the temperatures we're working with, ionic compounds are going to be solid. Unless this is in a solution, then it would be dissolved. So it really depends on the question. You'll get the hang of it. But if you don't see it's in a solution, if you have an ionic compound, it's going to be solid because ionic compounds, you may have learned, have very high melting points. So it takes a very high temperature to actually get them into their liquid form or to whatever form. They could be aqueous, just meaning dissolved, but in this case, it doesn't look like it was a solution. It was just some solid calcium put into a flask with some fluorine gas. So typically, ionic are going to be solid, so it's a safe assumption to make unless otherwise told. Follow the periodic table for your other states of elements. And remember the Hofbrinkel and the polyatomic ion or the polyatomic molecule rules that we discussed in previous lessons and also briefly reviewed in this lesson here. So again, the two types of equations we saw in this lesson were word equations and skeleton equations. The word equations, they actually identify the products and reactants as words, but they're a little bit longer to write, and they don't really give you useful information about the chemical, about their state. So what we do is we go to skeleton equations, which make them more universal. Everyone understands them because of their symbols and their formulas, and they give you more information about the chemicals, for example, their states.